Great, welcome everybody. We're thrilled to have you for today's webinar. Our presenter today is Greg Johnson, who is the president of RBR. And the topic of today's presentation is the assessment of the RBRcoda T.ODO optode for both profiling and long-term deployments. Welcome, Greg. Good to see you.
Thanks, Dan, and thanks for getting up early on the West Coast. Thanks also to those other West Coast attendees. Liz Creed, see you out there, thank you. Great to have you here, and some of the East Coast folks as well, names that I recognize. I think our furthest afield on today's this session of the webinar is coming in from St. Petersburg. So greetings to our Russian neighbor to the far, let's say far east, although I think it's probably almost the same distance if we went to the far west as well. So we're going to talk just briefly today, probably about half an hour or so. If I can get the slides to go, there we go. About our optical dissolved oxygen sensor, which is actually a combined temperature and oxygen sensor. The reason being that if you want to do saturation measurements, you do need temperature. And we need to always compensate the foil, which is used for the temperature measurement, for the oxygen measurements. And so while we were at it, building an instrument that measures temperature just for compensation, we thought we might as well do an oceanographic quality temperature measurement. So the temperature is something that we present, and you really get two channels instead of just one. The sensor itself is quite small. We don't have a little hummingbird or insect in this picture to show you for scale, but it's about 28 millimeters in diameter and about 10 centimeters long, 100 millimeters long. We'll be talking today a little bit about the sensor technology, some field work and different applications, and then move through to questions. So the sensor, when it's in its standalone form, like all of our sensors, is called the RBRcoda, followed by some characters that indicate what it measures. And this one measures temperature and optical dissolved oxygen. It's very similar to the measurement performance of an Andra optode, which you might be familiar with. So its accuracy is 8 micromolar. The temperature accuracy is 2 millidegrees. So it is perfectly adequate as a good oceanographic temperature sensor. It's rated to 6,000 meters and is always made out of titanium. However, when you look at the differences with and try to compare against the Andra optode, you'll see that the Andra offers two different time constants. One is their what they call standard and we call slow, a 30-second time constant using a foil that's protected by a Teflon cover. And the second is the 8-second time constant, what they call fast, but we just call our standard one. We have, in addition to that, a fast foil that is really is fast for oxygen measurements with a 1-second time constant, typically used in profiling applications. The other substantial difference you'll see with an Andra optode is that RBR brings its pedigree of low power electronics to the fore, and the power consumption is about a quarter of that of the Andra optodes. So for deployments where you are limited by battery power, that can make a substantial difference. The reason, one of the fundamental things that drove our development here was indeed the power consumption, and making sure that when you have a CTD that only consumes a fraction of the power of electrode-based CTDs, that when you add an optode, if you added an Andra, then you wondered, why did you bother making the CTD so efficient? Because its power efficiency was demolished as a system by the optical sensor. However, with our own optode being only 25% of the power consumption, we now have the ability to make complete instruments with CTD and oxygen in long-lived packages. The MCBH connector that's at the far end of the sensor is 4 pins are used, power and ground, and you can power this sensor with nominal 12 volts. And when you do, the serial lines will immediately spring to life and start delivering data at 1 hertz. That's the out of the factory default mode, which we call streaming. You can change the sampling rate of streaming. So if you want it to run a little bit slower, you can do so. Or you can tell it not to give you any data autonomously itself, that you're going to ask for it, which is what we call polling. And so when you ask the instrument for a measurement, it will give you back one measurement only. What are the measurements it gives back? As I mentioned earlier, of course, we give temperature out. We are fundamentally measuring phase. That is, and I'll explain a little bit about what phase is shortly. And phase is a useful output if you're going to recalibrate or do fairly involved measurements yourself. More typically, of course, it would be concentration in micromoles per liter. And we have two different outputs of that. One is a measurement that is corrected for temperature. The second is corrected for temperature and also corrected for salinity, because the salinity of the water makes a difference to the oxygen concentration. The salinity value that you're deployed in can be set inside the instrument. So you tell the instrument the salinity here is 35, and the instrument will then take that into account. When you add this sensor onto our CTDs, then in a profiling application where the salinity is changing, the CTD will automatically compensate the oxygen measurement for that changing salinity. And then finally, if you simply want saturation, the sensor will also output oxygen saturation as a percentage, as you'd expect. Sometimes you'd like to have this integrated into a, not a full CTD, but a simple instrument that records, and that would be our RBR duet. You can see here in the foreground, the optode, which is about, again, the 28 millimeters. And in the background, the yellow housing of the instrument logger itself, which is just a little bit narrower, about 25 millimeters. Again, all the same measurement parameters, but this instrument is completely autonomous, logs internally, and runs off a single AA battery. It's got USB-C built in, and you can get quite long deployments out of this, available both in plastic and a titanium variant to go down to 6,000 meters in total. So how do we actually make this? Many of you, I'm sure, are familiar with oxygen measurements using Clark cells or galvanic electrode cells. This is using, this word optode is actually a made-up word from optical and electrode, and there is actually no electrode in the system whatsoever. What we're using here is a chemical marker called a luminophore, and that luminophore has been placed into a solid gel, placed onto a foil, and that luminophore has an interesting property that when you illuminate it, as in this first line, with blue light, you excite the molecule. The molecule has to give off that energy, and when it does, there's some efficiency loss and some heat and those kinds of things. And so it can't give off the same light that it received as a blue wavelength. It gives off a longer wavelength, lower energy, and gives off a red pulse of light. So if you are to flash this luminophore with blue light, then a little while later, you will get some red light coming out of it. Now, what's interesting about, there are a large number of luminophores, but what's interesting about the ones that we use in these foils is that the fluorescence or the luminescence that comes off can be quenched or reduced by the presence of certain other chemicals, and in this case, we're looking at oxygen. And so that's what happens in the second line, is that the luminophore is equally excited by that blue light, but the presence of the oxygen molecule absorbs that energy, and so there isn't any emission of light. Now, when you look at this on a per molecule basis, this is what's happening. When you look at it on the bulk basis, there are a large number of molecules, and some of them give off light and others don't. The overall bulk effect is that you get a peak of light coming off, it quenches, and that quenching time is proportional in the bulk to the amount of oxygen that's present. So if you can measure that quenching time, which happens in fractions, or well, it's in nanoseconds, then you can assess the amount of oxygen that's there. Measuring at that rate is extremely challenging and requires a lot of power to the electronics. So there's another way of doing it, and that is to measure the phase delay between the pulse of light that you emit, that you excite it with, and that pulse and decay that is emitted. And the time delay between the two, because we don't excite with actually a single pulse, we excite with a pulse train or a sine wave, then you look for that phase delay between the sine wave of the incoming light and the outgoing light. And that phase is what is proportional to oxygen. So I'm going to draw your attention to the second grouping first. What is this luminophore? Well, this is a porphyrin complex. It looks a bit like a benzene ring. And this is the one that we use in the foil for the regular and slow coda. Those have 8-second and 30-second time constants. The drift on this foil, that is to say the change in behavior with the passage of time, is very low, and so it's well suited to mooring deployments. You can also correct it with 1 or 2 point calibrations. In order to do the fast foil, we need a luminophore that is much more sensitive because we're going to illuminate it for a much shorter period of time, and we also need to be able to see all the way through it because we're not going to wait for the oxygen to diffuse through the foil, which is quite a slow process. So you'll see later on, I'll show you a photograph of the foil. The foils for the fast are almost transparent. They're very slightly tinged pink, as opposed to the foil for the regular foil is opaque. That fast foil has a 1 second time constant and reasonably high drift, 0.6 micromole per liter per month, assuming that you illuminate about 2.5 million samples. And that drift really is a function of how much light it sees. So if you keep it dark, it doesn't drift at all. If it's in your in your cupboard or in your drawer waiting for a deployment, you don't have to worry about drift then. But I wouldn't leave it exposed to sunlight, for instance, because it will drift under those circumstances. Here is the photograph of the 3 foils. You can see in the center that opaque pink foil. Actually, the same foil is used for the slow instrument on the right-hand side, but it's covered in a black Teflon membrane. That allows us to wipe it without the wiper causing any damage to the porphyrin complex. And that's really what accounts for the time constant difference, is the amount of time that the oxygen takes to diffuse through the Teflon. That left-hand one is the transparent foil that I mentioned, which if you were to look carefully, you can actually see the electronics on the inside of the instrument through that foil. It's so transparent. This graph here shows you the behavior of the 3 instruments when plunged into a bath with a big step change in oxygen. And you can see the blue trace is, of course, the slow, the orange trace is the standard, and the yellow trace is the fast foil. How do we calibrate it? Well, I mentioned being able to do a 1 or 2 point calibration, and that's quite true when you're in the field. But in the factory, we do a much more complete calibration. We calibrate over 49 points. And those points are distributed 7 in temperature and 7 in oxygen. The response of the foil is very dependent on temperature. So we calibrate from 1.5 to about 30 degrees and 0 to 120% in saturation. And then we fit a polynomial surface to that. Those residuals are always less than 4 micromole per liter. In temperature, it's our standard calibration from -5 to 35 that we do for all our thermistor channels, and you will get an accuracy of 2 milligrees in resultant there. The user calibration is easy to do using our Ruskin software that you might be connecting the instrument to. You make the instrument perform the same measurements in 2 different levels of oxygen. So you can take an oxygen bubbler, for instance, a fish tank bubbler, an aquarium bubbler like in the fish tank behind me, bubble that through a bucket of water, and that will saturate the water after 15 minutes, 30 minutes. And you can use that as a 100% saturation level. And then you can use sodium bisulfite to consume all the oxygen in that water, and that will give you a 0% level. When you look at that data in Ruskin, you'll have those 2 levels, and you simply indicate which level is used during which part of that deployment. and RBR will then, the Ruskin software will then calibrate those coefficients for you for the 2-point calibration, which is laid on top of that 49-point calibration. Here's what's going on inside the sensor. All the boxes in yellow are measurements that we're making that are available in the output. So we do have an amplitude light source inside, and we measure that, both its amplitude and the amplitude of the foil. We have the foil phase, as I talked about earlier, and also the reference phase. We correct the foil phase with the reference, which gets rid of most of the aging effects. And we have the foil temperature. And those are all available as outputs. But what you're really typically interested in is the oxygen concentration in the bottom left, or if you prefer it in saturation terms in the bottom right. The salinity compensation and pressure compensation that can also be applied can be done as well. Those are optional. And you can see in equation 4 that this is really just an arbitrary polynomial, arbitrary set of cubics. So there's some work done a couple of years ago, provided a nice data set. This is the Bedford Basin in Nova Scotia, about 1,500 kilometers east of here on the east coast of Canada. It's just off from, sandwiched between really the Department of Fisheries and Oceans Bedford Institute of Oceanography, BIO, and Dalhousie University in Halifax. There was a deployment done there in 2018 on the bottom of this subsea buoy. And so this was deployed in, I believe it's 80 meters of water. It was just above the bottom, so probably in about 60 meters water depth. And we've got to thank Dalhousie and DFO for making this happen. It was a nice buoy setup because it had a number of instruments on it. Not only our CODA that's in the foreground, but they also had a Seabird 37 and a few other sensors. I think the Seabird 43 oxygen sensor was there as well, and deployed for 4 months. Each week, the Bedford Basin Monitoring Program also takes a boat out and it goes over the mooring and does a CTD cast. And so our CTD, along with 2 other oxygen sensors, were also used in the profiling application. And we have some profiles from this showing both the 8-second and the 1-second side by side. Yes, you can imagine what's happening. It's showing you temperature on a scale of degrees. Doesn't show you very much, I'm afraid, but although it appears to be one color, of course, both the Seabird and the RBR are able to measure temperature to a millidegree level of accuracy. So they appear to be overlaid. Dissolved oxygen, so you can see big seasonal, big shifts here, about 2 milliliters per liter. And we have the RBR in red, the Seabird 43, which is a pump system and requires quite a lot of power, producing those blue triangles, well aligned, and the bottle samples as well that were taken. And the alignment's quite good. When you look at the profiling results, you can see clearly the difference in time constant between the ODO standard and the ODO fast. So that blue curve is the smooth curve because that time constant is about 8 seconds. And we're profiling at close to a meter per second. When you look at the 43, which is pumped, along with our fast soil, which doesn't require a pump, you see very good alignments between those two. Unfortunately, with the bottle samples, there are only 2 of them taken, and so not much to compare with. If you do use a standard optode for profiling, you can actually improve the results if you are willing to take the time to correct. And that correction constitutes sharpening the temperature reading or using the FOSDOR kind of sharpening algorithms. I would generally say that that's not advised. We would generally say use the fast optode to get the right measurement at the right time constant. But it does go to show that effectively you're able to deconvolve the slow behavior. And as long as that drop rate is constant, you'll be able to get improved results this way if you're interested in doing that. The advantage of the standard over the fast is that much lower drift characteristic. So if you're in a situation where you're profiling, but repeatedly over a long period of time, for instance, on a wire walker or an Argo float, then using the standard thermistor with its lower drift is a much better approach. So the slow is really best suited for the mooring applications, the fast is best suited for profiling applications, and the standard falls somewhere in between, depending on whether the low drift or the fast performance is necessary for what you're looking at. And we've got to thank Richard Davis at Dalhousie and Clark and the Sigma T crew at BIO for doing that work a couple of years ago. So in terms of integrations on instruments, of course, profiling is an obvious one, and mooring applications on the right. But there are also vehicles and floats into which the ODO has been integrated. On the standalone instruments, our RBR Concerto is able to support an additional 2 sensors beyond the CTD. And so in this render in the center, you can see temperature, conductivity and pressure on the end cap, dissolved oxygen on the left-hand side in the clamp, and turbidity in the right-hand side. So an ideal instrument for kind of coastal measurements. That could be deployed either standalone like that, or if you need to protect it against boat handling, then deploy it inside a cage. Nature Trust in BC here is doing a number of estuarine studies just inland from the Pacific. Deployments on floats are also common. You'll notice that this one, which is on top of the MRV Alto float intended for the Argo program, the sensor appears to be longer than those pictures you've seen earlier, and that's correct. It is. It's because we're following the TODO recommendation for having 20 centimeters of freeboard between the waterline and the oxygen sensor, so that when we're at the surface, we're able to make a surface air measurement to ensure that you can assess drift over the lifetime of the float, which might be 4 or 5 years. It's also been attached to a number of gliders. You may have seen it on the Kongsberg/Hydroid/Huntington Ingalls etc. Sea glider. I think we've also seen it on the Slocum glider. Here's some data from China in the South China Sea, where it's deployed on the AMT Haiyan glider and producing very nice profiles over a series of, I think that's about a month of transit. The custom ODO sensors have also been done, and this one for a vehicle with right angle flow through a tube inside the hull of an autonomous boat. In mooring deployments, I mentioned the use of a wiper earlier, and you can see in the render the way this automatic toothbrush, if you like, cleans that surface. And the photograph on the left, you can see that everything gets fouled. This is in Lake Tahoe, which is an extremely clear and fairly low biological activity lake in the United States. But the optode surface itself is kept very clear, even though the toothbrush itself is completely covered in algae. So that's a very brief run-through of the RBR optode, and I'd be happy to ask any questions or talk about deployments. Thanks for coming.
Greg, thanks for the presentation. Alice Parks had a couple of questions in the chat window. Are you able to see those?
Yeah, I can. So let's see. Does the temperature of calibration influence the accuracy of the measurement? Calibration. No, because we know the temperature at which the calibration is done, we can actually apply it correctly. So it shifts the whole, if you imagine that two-dimensional surface that we're fitting, it takes the whole two-dimensional surface and offsets it according to the location and temperature where we're making the measurement during the calibration. So you can do it with a bucket of water in the lab, or you can do it with a bucket that you've just pulled out from alongside the ship that might be much colder, or something, you could even calibrate it with water that's come back in a bottle sample. So that's really what is, yes, no problem with calibrating at any temperature. And Alice also asks, at what speed were the profiles performed? And so those were at 1 meter per second, just off a small boat. Which is kind of nominal for the people we're working with. Argo floats, of course, are profiling much slower at 10 centimeters per second. And wire walkers, which are commonly used, are kind of halfway in between. Typically, they're set up so their buoyancy drives them up at about 50 centimeters per second. So none of those rates are particularly high. It's not like a free fall CTT that might be running at 4 or 5 meters per second, or something that's going to turn into a gravity core by the time it hits the bottom. But all of them are sufficient to have perfectly adequate flushing. And of course, with an optode, well, the issue with an electrode-based galvanic cell is they typically have very good time constants, but they consume the oxygen they're measuring. And so you must, in a moored application, agitate somehow. Either by having a pump or by hoping that you've got enough current going past the mooring. Because if I was to stick a Clark cell into a beaker of water and leave it to measure, you will see the apparent oxygen fall away as it's consumed on the electrodes. In the optode, there is no oxygen reaction that's happening. It's just this excitation of the luminophore. And so you don't need a flushing system in order to ensure that you get a good measurement. I hope that answers the question there, Alice. Any other questions? It might be lunchtime for too many people, and we're all keen to get.
You're welcome to unmute themselves and ask a question directly, or put it in the chat window.
Yeah, I just had a question about the name optode. I thought that was specific to the Andorra sensor, but it sounds like maybe that's specific to this type of instrument built by different companies.
That's right. So optode is a general term. You can find it, well, we don't go to encyclopedias anymore, we go to Wikipedias, but yes, if you look up optode, you'll find that it is a generic term for any kind of optical measurement. There are optodes for different species of measurement. So for instance, you can make a carbon dioxide optode. You can even make a pH optode. Because there are luminophores which are sensitive to changes in pH value or hydrogen ions rather than oxygen presence. But of course, optode has been used so generically for, and I would say predominantly, for the main oxygen optode, which has been around for a number of times from Andorra, that it's almost like Kleenex and it gets used synonymously with the Andorra optode. Andorra themselves actually, I don't know whether they ever released it to market, but I know I've seen an engineering version of their carbon dioxide optode, which they also call an optode. So yes, it can be a bit confusing at times. The same would be true now. The Seabird 43 is a galvanic cell, but the Seabird 63 is Seabird's oxygen optode. And in fact, for our 8-second and 30-second sensors, Andorra, Seabird, and RBR are all using exactly the same foil. So providing none of us really screws up the electronics, the measurement accuracy should be roughly similar. I think all of us are quite capable of calibrating. The real difference comes in power consumption and reliability and pressure rating, those kinds of things. But the foils are actually identical. Our fast foil is one that isn't available on the open market from other people. From St. Petersburg, Do we use a monitoring system in a fish aquarium? So this is our coral tank. It actually looks a little bit, well, no, there's some decent stuff to see from this side of the room, but outside is our visitors area, and it's out there. We don't have a monitoring system in here at the moment. We've just moved into this office in the last 2 or 3 months. And we keep on thinking, yes, we should do a number of things. We've got a sump tank underneath, and we're thinking about having a nursery tank soon, because the clownfish, if you don't know what a clownfish is, you might know it as Finding Nemo fish. And the larger one there is the female, smaller one is the male. They love laying eggs in the, I think it's called bubble corals or fingertip corals. And so we are always tempted. Of course, the eggs then get eaten by all the other fish. So we're going to have a nursery tank and start breeding, just because we've got so much spare time. Piero.
Is there a question being asked right now?
So I can see a question from Piero, but I will, Alice, I can take your question afterwards. So Piero says, are you guys working on a method for maintaining the foils clean for fast oxygen, thinking about long-term deployments on the wire walker? So it's actually quite tricky, Piero, because the fast foil is so thin, as you saw, it's almost transparent, and it's also very fragile. So if you were to rub it, it will come off. The obvious candidate for keeping fouling away would be ultraviolet light. But unfortunately, ultraviolet light interacts with the luminophores and bleaches them. Just like you can think of, it's not the same process as coral bleaching, but it's effectively a sunburn. And that means that the luminophore isn't as effective over time. It's almost the same as leaving it out in the sun. So UV is not a good candidate for anti-fouling the fast foil either. Really, in that application, I would use the standard foil, actually, yeah. So most people with wire walkers, it's got to be said, are deploying for about a month in between maintenance intervals. And so I would go and clean the instrument at that point. You can also put copper tape around the foil itself, so not the actual foil dot, but the rest of the titanium. Fouling is also reduced on the wire walker just because of the higher speeds. 50 centimeters per second doesn't stop everything from grabbing on, but certainly it's not as easy as it is if you are in a moored deployment. I hope that answers the question there, Piero. Alice, you want to jump in?
Yeah, I was just wondering if, I think you went quickly through it, we can receive the data in phase and in concentration and in saturation?
That's correct.
And you provide the equations to convert among those three?
Yes, although they're absolutely standard ones. So saturation to concentration and vice versa is Garcia-Gordon, and which way around is it, the other one? Is it Techno 44? Anyway, yes, we can supply those. We've actually got a MATLAB toolkit called RSK tools, and that has those built in. So if you don't want to re-implement the equation yourself, you can just read the code. That's not hidden in any way. Our Ruskin software, if you give it a channel that was only saturation, it will derive concentration for you, or if you give it concentration, it will derive saturation for you. So yes, you can either tell the sensor, give me it yourself, and the sensor will do the hard work, or you can do the work in post-processing using either of our tools, or of course, implement your own. There are many toolboxes in Python or R or whatever where people have implemented those.
Greg, you talked about field-based calibration or two-point calibration that's done through Ruskin. Can you talk a bit more about maintenance and or servicing requirements of the optical dissolved oxygen sensor?
Yeah, there really is nothing else actually, apart from keeping it clear of buildup There's no reason for it to come back to RBR for regular calibration. That 2-point calibration is perfectly adequate over for as long as you own the sensor. It's not like a CTD where it really benefits from annual calibration. This benefits from annual calibration or more frequent calibration, but that you should do yourselves. 1 and 2-point calibration, sending it back to RBR is an expensive way to get it done when you can do it in your own lab. And of course, most countries have national facilities which are able to do the fuller calibration. If you want to do the multi-point calibration again, for instance, Cesaro in Australia, Ifremer in France, Jamstech in Japan, NCOSM in China, and then Scripps actually has a very nice kind of oxygen calibration box. And I think the design is semi-open source. You find it often on ships around the world where they've got everything they need in a small carry case. And you can do Winkler titrations yourself.
Thank you. Any other questions for Greg today from the group?
Let's leave it at that then.
Yep.
Thank you very much.
Thanks everyone for joining us. We look forward to seeing you at future webinars with RBR. Bye-bye.
Bye now.